Hi, my name is Xiong Xiao. It's my pleasure to present our speaker derivation system for the VoxCeleb Speaker Recognition Challenge 2020. You can also find our system description at the following archive link. Speaker derivation is still a challenging task due to a few reasons. First, speaker embedding is affected by many factors other than the speaker characteristics. For example, environmental factors and language factors. Overlapped speech also causes a big challenge. Without proper handling of overlapped speech, a high miss error rate is guaranteed. To address above challenges, we propose a system with improved speaker embedding using Res2Net model and AM noise, and also conformer-based continuous speech separation with leakage filtering, and a system fusion with modified Dover. Here is a system diagram. The continuous speech separation separates input audio into two channels, regardless of whether there is overlap in the audio. Then speaker embedding is extracted and the segmentation is performed. The segments from both channels are then fed into the speaker clustering. Multiple systems can be combined by using modified Dover. The conformer introduces a convolution block in the transformer structure, where self-attention is good at capturing global information. The convolution layer is expected to improve the model's ability to learn from local information. We also adopted the continuous speech separation framework that performs separation in overlapping chunks and then stitch the outputs together. Please see reference 1 for more information of our speech separation system. To improve speaker embedding, we used the Res2Net model structure. The channels of the input feature map is divided into several groups and individually convolved with filters. Residual connections between the groups help representing multi-scale information. We also use the additive margin softmax cost function to improve the discrimination between speaker classes. Our best model achieves 0.83 equal error rate on the Vox1 test set. Both segmentation and clustering are implemented by AHC. One major difference is that in segmentation, only consecutive segments can be merged. For clustering, we use a very high threshold to ensure high purity in the clusters. This results in under-clustering. That is, the number of clusters is usually much larger than the number of actual speakers. Then only those clusters that are longer than the predefined duration threshold are considered as speaker clusters. The rest of the clusters are then assigned to those speaker clusters using cosine similarity. If a cluster is not similar to any of those speaker clusters, it is assigned to a special class called unassigned cluster. This class is currently treated as a single cluster in DER computation. We found that speech separation occasionally generates leakage, such as residual noise and music. VAD may fail to reject those leakages and causes false alarm. To solve this problem, we introduced a leakage filtering method. We first run derivation on original audio and obtain the cluster centroids. We assume that these cluster centroids are a good representation of the speakers in the audio. Then we run derivation on the separated of speech. For every segment, we compute its cosine similarity with the cluster centroids from the original audio. If a segment is not similar to any of those clusters, it is removed from the final derivation output. This method is very effective in removing non-speech leakages, such as music and noise. Dover is a system fusion method for derivation. We extend the Dover to handle diarization output from separated audios and call it the modified Dover. Let's use an example to explain the modified Dover. Suppose we have three diarization systems called alpha, beta, gamma, as shown in the figure. The first step is to find the root hypothesis. In our system, the best single system is used as the root hypothesis. Then the other system hypotheses are aligned to the root hypothesis independently. The alignment involves finding the best speaker mapping between the two hypotheses using the Hungarian algorithm. If a system has more speakers than the root hypothesis, extra speakers are discarded after the mapping. After all hypotheses are aligned with the root hypothesis, for each speaker and each time step, the final speaker activity is decided by voting. Let's move to the results. First, let's look at the impact of the speaker embedding model. As shown in the table, there is a high correlation between the equal error rate and the DER, meaning that the speaker diarization and the speaker verification tasks are highly related. The best model has a larger size and trained with more data. Let's move on to the effects of the speech separation. System 4 applied speech separation but without leakage filtering. The gain of the speech separation is largely offset by the false alarm caused by leakage. After leakage filtering is applied, we see big improvements in DER in both dev and test sets. This shows the importance of the leakage filtering, at least for our system. Until now, the AHC parameters are tuned from other diarization tasks. After fine-tuning with the challenge dev set, the DER is reduced a bit, but the JER is reduced significantly. Finally, we fuse 4 systems using the modified Dover. Mixed results are observed on the test set. Big improvements on DER, but degradation on JER. We are not clear about the reason for the error pattern due to limited data points. Speech separation is important for dealing with overlapped regions. It's important to have leakage filtering to obtain the gain of the separation, at least for our specific system. The quality of speaker embedding is crucial for good diarization performance, and system fusion with modified Dover is a general way to boost the diarization performance. Thank you.